So what I have over here is a uniform rod with the length of L, and the rod lies on the x-axis. And the rod is centered at the origin, and the origin is right here, which is shown in the red dot. And so one end of the rod lies at the x-coordinate L divided by 2, and the other end of the rod lies at the x-coordinate negative L over 2. And so what I want to do is I want to find what is the gravitational field at point P, which is on the x-axis, but it's a distance away from the rod. So I want to find what is the gravitational field due to this entire uniform rod at point P. Now, in order to solve this, let's consider a similar scenario. Let's say instead of a rod, let's look at a circular mass with the mass of lowercase m. And let's say I want to find the gravitational field at a point P that is a distance away from the mass m. So instead of looking at a rod, I'm just going to look at this different scenario with a circular mass. I want to find what is the gravitational field at this point P, which I circled, due to this mass m. Now, and so I denoted the gravitational field at point P with G subscript P. Now, in order to solve this, what we have to do is we need to place an arbitrary mass at point P. And I'll just label this arbitrary point mass with a capital M. And so this is just an arbitrary point mass at point P. Now, why did I place an arbitrary point mass at point P? And so the reason why I did this is because we can now find the gravitational force acting on the point particle due to the other mass. So let's call that gravitational force F. And we want to find the gravitational force acting on the point mass due to the other mass m. And if we can find this gravitational force of attraction between these two masses, that can help us find the gravitational field at point P. And so we want to find the gravitational field at point P, and in order to do this, the gravitational field at point P is equal to the gravitational force of attraction between this mass and this arbitrary mass. And remember that the capital M is just an arbitrary mass that I just arbitrarily placed at point P, which is the point of interest because we want to find the gravitational field at that point. And so we want to find what is the force of attraction between this lowercase mass m and the capital letter M, which is the arbitrary mass. And since I arbitrarily put a mass at point P, I want to get rid of that mass. So what I'm going to do is I'm going to divide by the capital letter M. And so this is essentially the definition of a gravitational field at some point. Let's say if we have a mass and we want to find the gravitational field at some point away from that mass, we can just put an arbitrary point mass at that point and then divide by that arbitrary point mass. Now let's expand this equation out. Now, the equation for the gravitational force of attraction between two masses involves the distance between the two masses. So we had to take that distance into account. Let's say that the distance between the two masses is given by x. And so, or the distance from point P to the other mass is x. And let's say that the direction in which the gravitational field is pointing at point P is that it points in the left direction, or it points in the direction of the mass. And the reason why it points towards the lowercase letter m is because it is attracted to that mass m. Or in other words, the arbitrary point mass m feels a force of attraction towards the lowercase letter m. So that's why the gravitational field at point P points in the left direction. It points towards the lowercase letter m due to it being attracted to that letter m. And so the equation for the force of attraction between the lowercase letter m and the capital M is that it equals the gravitational constant times one of the masses and times the other mass divided by the distance between them, which is x, and then it's squared. And remember that we're dividing by m, and notice that both these m's, the capital letter M, cancels out. And so the arbitrary point mass, which is the capital letter M, gets canceled out. And the only mass that we're left with is the lowercase letter m. And also note how the gravitational field at point P points in the left direction, or it points towards the lowercase letter m. And since it's a vector, we have to take that direction into account. So the sign on this equation right here is going to be a negative sign, since the gravitational vector points in the left direction. And so we're considering the left direction, we're considering that to be negative, and we're considering a vector that points to the right to be positive. And so the gravitational field at point P, due to the lowercase letter mass m, is given by this final equation right here. And so this is essentially the gravitational field at point P due to the mass m. And notice how we first started out by placing an arbitrary point mass at point P. And that was an arbitrary mass. And then later on, we divided that mass, and then notice how that arbitrary mass canceled out. So these two variables right here, the capital M and the other capital M, they both canceled out because that was an arbitrary mass. And so the mass that we really care about, or the mass that we really want to take into consideration, is the lowercase letter m. Now let's apply what we know to this segment right here, the segment with a width of dx. Now this is a small element on the uniform rod, and it has a width of dx, and it has a mass of dm. And this small mass of dm is going to produce a small gravitational field at point P, which is denoted with the dg. So we can apply this equation right here to the small mass dm for the uniform rod above. So if we apply that equation to dm, we're going to get the following. We get that dg is equal to a negative sign, since the gravitational field vector at point P points in the left direction. So we're considering the left direction vector to be negative, times the universal gravitational constant, which is capital G, times the mass that we're considering. And the mass in this case is a small mass element dm, which is circled in red. And we're dividing that by the distance between point P and the mass element dm. And let's say that distance from the mass element to point P is given by x. And so we're just going to square x. And so essentially, another way to look at it is that the gravitational field due to a small element on the rod with a mass of dm is given by this equation right here. But now that's only for a singular element. What about the entire rod? We want to find the gravitational field due to the entire rod, not just a singular element on the rod. So another way to think about that is that we can cut up the rod into really small pieces, and each of these pieces is going to have a mass of dm, and each of these small masses are going to produce their own gravitational field at point P. And that gravitational field is going to be denoted with this left vector dg. And let's consider this other mass element dm. That's also going to produce its own gravitational field at point P dg. And so each of these really small elements of dm are going to produce their own gravitational field at point P. And so what we want to do is we want to find the individual gravitational field due to all of these small dm elements, or these dm segments, and then we want to add all these individual gravitational fields at point P to get a total net gravitational field at point P. So essentially, another way to think about it is that each of these small mass elements are going to produce their own small gravitational field at point P. And if we consider another small mass element, let's notice how there's many small mass elements. If we consider any other small mass element, it's going to produce its own gravitational field at point P, and it's a really small amount of gravitational field. That's why I denoted it with a dg. And if we continuously add all of these small elements, then we're going to get the total mass of the rod, which is denoted with m, and we're going to get the total gravitational field at point P. And so this G represents the total gravitational field at point P due to the uniform rod. And adding up all these small dm elements gets us a total mass for the rod, which is m. Now let's apply this concept of adding all of the individual dm elements to give us a total mass m, and adding up all of the individual dg gravitational elements to give us a total gravitational field at point P to solve this question. And so essentially, when we're finding all of these small elements and when we're adding up all these elements, we're essentially taking the integral. And by taking the integral, we're summing up all of these individual small components to give us a total net or a total resulting value. And so let's apply this to this scenario to give us a gravitational field at point P due to the entire uniform rod. And so now the equation that you see on the screen is just the gravitational field due to a singular mass element dm, but we want to get the total gravitational field due to the entire uniform rod. Now, first, let's come up with the alternative expression for dm in terms of our other given variables. Notice how the entire mass of the rod is capital M, and the total length of the rod is L. And notice how the mass of a small segment on the rod is dm, and the width of a small segment on the rod is dx. Now we can use these four variables to write a proportion. So the ratio of dm to dx is equal to the ratio between the total mass, which is capital M, to the total length, which is L. Now if we solve for m, or dm, we get the following. Now we can just plug in this equation into our earlier formula. So we can just plug in this alternative expression for dm into this formula up here. Plugging that in, we get the following. And so notice that each of these small elements of mass dm produce their own small gravitational field at point P, which is labeled with dg. And so to find the total gravitational field at point P, we have to integrate the entire length of the rod, or we have to integrate over the entire length of the rod, and by doing that we essentially are adding all of the individual small elements of the gravitational field at point P to get a total net gravitational field at point P. And so what does this mean? And so each of these small mass elements are going to produce their own gravitational field at point P. If we add up all of those individual small gravitational fields at point P, we can get the total net gravitational field at point P, which is the same as taking the integral, since we're summing all of the small gravitational fields. And so we have to take the integral of both sides of this equation. And if we do that, it would look something like this. And notice how this entire expression right here is just a constant. So we can take those out of the integral since these variables are just constants. So we can pull that out of the integral expression. And so the only thing we're left with is the integral of x squared. But notice how in our integral of 1 over x squared, we need the limits of integration. Or we need an upper limit and we need a lower limit. And notice how earlier we were breaking up this uniform rod into smaller and smaller pieces, and the point at which we or the point at which the rod starts at is given right here by this long line segment right here shown in red, and that's at the x coordinate L divided by 2, and that's the beginning of the rod. And so since that's the beginning of the rod, that has to be the starting point of our integration. And this marker right here, shown in red, which is at negative L over 2, that's the ending point of our integration, since that's where the rod ends. So this entire length right here is given by L, and we're integrating over this entire length. So this is the starting point, which is L divided by 2, and the ending point is at negative L over 2. Now let's take those x coordinates in, or let's take those positions into our integral expression. So what's the distance from this starting position to the point P? So the distance from the starting position of the uniform rod to the point P is given by the variable x, as shown right here. Now what about the distance from negative L over 2 to the point P? So we know that the length of the entire rod is L, and to get the entire length of the distance from point P to the end of the rod, it would just be these two distances added together. So this right here that I just drew, that's the distance from point P to the end of the rod. So we know that the end of the rod is L, and we know that this distance right here is x. And so we said that the initial starting point of our integration is x. And so the final upper limit of integration is just going to be L plus x, or the combination of these two variables. So the lower limit is x equals x, since that's the starting position of our integration, and the upper limit is x equals L plus x. Since the rod is the end of the rod is a distance L plus x away from the point P, and the starting point of the rod is at a distance x from point P. So essentially we're just looking at how far is the start of the rod from point P and how far is the end of the rod from point P. That's how I came up with these upper limits and lower limits of integration. Now let's solve what is the integral of dg right here. Now the integral of dg would just give us, is essentially saying what do we get when we add all of the individual gravitational fields due to the small mass elements at point P? Or what is the net gravitational field at point P due to each of the small mass elements? And that would just give us the gravitational field at point P, which is denoted with GP. And so what is the integral of 1 over x squared? And the integral of 1 over x squared is just 1 over x. And we have to take the limits of integration into account. The lower limit is x equals x, and the upper limit is L plus x. Now, all we have to do is plug in this upper limit into our result for the integral, and we have to plug in the lower limit into our result for the integral. Now let's plug in the upper limit. If we plug in the upper limit in for x, we get this, and notice how there's a negative sign in front of the 1 over x, so we had to subtract a negative, so it would be minus minus, and then we have to plug in the variable x, or we have to plug in the lower limit of integration into our result for the integral. And a minus minus just gives us a positive. And so the gravitational field, or the total gravitational field at point P, is just given by this expression right here. And so let's combine these two fractions into one fraction, and we can do that by cross multiplying the numerator of one fraction and then multiply by the denominator of the other fraction, and then multiply the denominator of the other fraction by the numerator of the other. If we do that, we get this. So let's multiply -1 by this denominator, and let's multiply this denominator by the numerator of the other fraction, and we get this. And then finally, the denominator of the result would just be L plus x times x. So that would look something like this. And notice how -x plus x would just give us 0. And so all we're left with is L for the numerator. And if we distribute this x into the parentheses, we get the following. And notice how both these L's cancel out. And so the result that we're left with is the following. So the total gravitational field at point P, or at any point P that lies on the x-axis, is given by this final result right here, -g times the mass of the rod divided by x squared plus x times L. So this is the net resulting gravitational field at any point on the x-axis. And notice how this answer is negative, because if we consider the point on the x-axis, the gravitational field at that point is going to point towards the rod, since that point is feeling an attraction towards the rod. So the gravitational field vector at point P is going to point in the direction of the mass of the rod, since it's attracted to the mass of the rod. And that's why in this case, the gravitational field at point P is negative, because the vector points in the left direction, in the direction of the mass of the rod.